Good afternoon, everyone. Welcome to the third and final press conference of this first day of the 235th meeting of the American Astronomical Society, but we have 6 more briefings over the next 3 days, so don't give up on us yet. I'm Rick Fienberg. I'm the press officer of the AAS. We're webcasting this session, as usual, and assisting me by monitoring the webcast is my AAS media fellow, Tharini Conchadi, in the back of the room. She'll be relaying questions from online viewers. Please silence your cell phones, or just make sure they're not going to ring on us. And this is a seminar for science writers, which is a little different than a press conference. You're not going to hear a lot of breaking news, though there are quite a few Hubble results being presented at the briefings over the next couple of days, and we had one already this morning. But this is about the future. We're celebrating the past. We're celebrating 30 years of Hubble in orbit as of April. But rather than look back and let the telescope rest on its substantial laurels, we're going to look ahead at this functioning, state-of-the-art observatory that's going to continue to produce exciting science over the next decade and who knows how long. And we have this seminar was organized for us by the Space Telescope Science Institute, principally Ray Villard here, who will be speaking last. And he's assembled a stellar, even a galactic team of experts, of people who have used the Hubble Space Telescope and look forward to continuing to use the Hubble Space Telescope. And they will speak in the following order. We'll start with Jennifer Wiseman from NASA Goddard. She's going to speak on Hubble's top accomplishments, current status, and planned science for the 2020s. She'll be followed by Nikole Lewis from Cornell University, who will speak on Hubble's characterization of exoplanets and future observing strategies. Then Heidi Hammel from the Association of Universities for Research in Astronomy will speak on Hubble's ongoing monitoring of solar system planets and minor bodies. Garth Illingworth from the University of California, Santa Cruz and Lick Observatory will speak on Hubble's deep sky surveys and planned synergies with the James Webb Space Telescope and the WFIRST Space Telescope. And finally, Ray will talk a little bit about Hubble as a cultural icon, which we all know it is. And Ray, of course, is at the Space Telescope Science Institute. So with that, we will get started. I'll turn it over to Jennifer.
Thank you. So welcome to this seminar. This year we are celebrating Hubble's 30th birthday. So it's a very exciting year, and we're excited about it because Hubble is in tremendous shape right now, technically and scientifically. It's very powerful. So we have a lot to celebrate about Hubble's past, its present, and its future. My talk is just going to give you a little bit of background as to where we are in terms of Hubble's science and status, because I suspect that some of you in the room are younger than Hubble, or you don't really remember much of Hubble's early years, and some of you remember those years very well. But I just kind of wanted to get us all on the same footing here for the detailed presentations that will come after me. Hubble was launched in 1990. Here are some of the stats there. It is a satellite in low Earth orbit around the Earth, whizzing around at about 17,000 miles an hour, but pointing very precisely at distant stars and galaxies and planets that we want to study scientifically. It's a partnership between NASA and the European Space Agency, and we continue to enjoy that partnership today. We've become accustomed to these marvelous images. In fact, the world is spoiled by the images that Hubble has provided. This is the 25th anniversary image of a star-forming region known as Westerland 2, showing off Hubble's capabilities and the beautiful dynamics of star formation in our galaxy. Why do we have a space telescope? Well, this was formulated for decades before Hubble was ever launched. There's a rich history of this, which I'll just mention a couple of things. Lyman Spitzer's committee recommended what you would do with a large space telescope for a National Academy study in the 1960s. Then in the 1970s, Nancy Grace Roman, who was in leadership at NASA headquarters, put together everything that was needed for the first announcement of opportunity for science and instruments that might go aboard such a space telescope. And just as an aside, some of those early designs for a space telescope had the astronomer actually at the telescope. So wouldn't that have been fun? But it turned out that's a little impractical. So we're actually transmitting commands and up and data back down. Darn it, that's so much more boring. It was launched on the space shuttle. And as some of you may recall, or some of you may have heard, the original images from Hubble were a bit disappointing. So even today, the lore of Hubble includes the dramatic story of the initial disappointments of the Hubble Space Telescope, because the mirror was ground very precisely to a wrong formula. But it was repaired in a very dramatic astronaut repair mission the third year after it was launched, and it was a successful repair. And now all the instruments that have been put on Hubble ever since have optical corrections built in. So everything since then has been pretty much perfect on the observatory in terms of the science data that we get. And in fact, we've had a whole litany of astronaut servicing missions, which is why we can celebrate Hubble's 30th birthday, knowing that Hubble is still very healthy, and we anticipate it being scientifically productive for many years to come. So this litany of astronaut servicing missions has enabled repairs of the observatory and also enhancements by putting in new science instruments, and has extended Hubble's mission life by many years. Here's the succession of Hubble missions, servicing missions over the years, including lists under each of those pictures of the kinds of instruments that were either repaired or installed during those missions. The last one we did was in 2009, and the astronauts did a fantastic job on that mission, so the observatory is in great shape even today. We're benefiting from the fact that Hubble is above the Earth's atmosphere, because our atmosphere, our turbulent atmosphere, can blur images taken from light traveling through that turbulent atmosphere. And so an observatory above the atmosphere can get very sharp resolution. So here's an example of the core of a very compact, dense globular cluster, Omega Centauri, but you can differentiate star from star in this crowded core because of Hubble's angular resolution. And that is one of the reasons that we have this observatory above the atmosphere. Hubble is in good technical condition and is right now, even after 30 years, just about, the anniversary will be in April, but it is at the peak of its scientific return right now. And it is a full observatory with a whole suite of cameras and spectrographs, as you can see on the diagram there. Here's an example of why it's good to have both cameras and spectrographs. So this is Eta Carina, very unstable and active binary star system with a lot of explosive events, which you can see with the camera on the left side of the image, in this case the WFIRST-2 camera image, and the spectrum from this region taken with the STIS spectrograph on Hubble, which tells you about the composition of the gases and the material in this system and the motions of the material as well. So having cameras and spectrographs gives you a very powerful combination of scientific tools on the Hubble Space Telescope. Hubble also has panchromatic capabilities. We can see electromagnetic radiation from the ultraviolet, which is more energetic than visible light, through the whole visible light spectrum and into the near part of the infrared spectrum. Here's a visible light image of the Eagle Nebula, very famously imaged view from Hubble. This is a newer image taken with the newest camera on Hubble in visible light. But if you look at that same region with that Wide Field Camera 3's infrared capabilities, which is on the right there, you can see through a lot of the dusty veil and see these active regions of star formation in those columns, as well as many more stars. I won't say much about Jupiter because Dr. Hammel here will be telling you more, but here's a visible light image of Jupiter, and I wanted to point out that one of the other powerful reasons we have Hubble is that Hubble, especially now, is providing us the only sort of general purpose ultraviolet light observing capability that we have now, and even in the foreseeable near future for now. And there's some proposals here at this conference for missions that might follow Hubble in terms of having ultraviolet light capabilities. But we have to be above the atmosphere to observe ultraviolet light, and Hubble is doing that. In particular, Heidi, I'm sure, will tell you about the ultraviolet light auroras there on Jupiter. All right, we're using all these capabilities to look at galaxies and cosmology. Here's the famous ultra-deep field. And by looking at galaxies in infrared light as well as visible and ultraviolet light, we can understand very much about the history of galaxies in the universe and star formation histories within them. So Hubble has made well over 1 million observations since it's launched, well over 15,000 published papers. It's had a whole litany of major discoveries in terms of really confirming that there are black holes in the centers of galaxies. It has measured the expansion rate of the universe, and the refinement of that measurement continues to this day. It has been the pioneer in measuring the composition of exoplanet atmospheres. We'll hear more about that from Dr. Lewis. And we have also used Hubble to study about star formation and protoplanetary disks around stars. That's opened up an entire new field. But we're also using Hubble to investigate big questions about the universe that were not anticipated when Hubble was originally launched. Like, what is dark energy? What is dark matter? Where is it? And are there other planets like Earth in the universe, in the galaxy? Things about our solar system, even studying radiation from the sources of gravitational waves. These were not thought of when Hubble was launched. A Nobel Prize has been awarded for investigators who use telescopes, including Hubble, to determine that the expansion of the universe is accelerating by dark energy. Dark matter, which is unseen but is prevalent in these clusters of galaxies, is distorting light from background galaxies, teaching us about those background galaxies and also about the distribution of dark matter within the clusters. Exoplanet atmospheres. Hubble's capabilities complement those of other ground-based and space-based telescopes and probes. This is really important. We need Hubble. We also need other telescopes in space and on the ground and other probes in the solar system to give us a full understanding of what it is we want to study. The Hubble Space Telescope's mission continues now with strong scientific capability, likely through the 2020s, and if you're optimistic, maybe beyond. And its scientific capabilities complement current and future missions like the James Webb Space Telescope, which is due to launch next year. I won't say too much more about the details of Hubble compared to James Webb, but they do cover slightly overlapping but mostly different parts of the electromagnetic spectrum, with Webb being an infrared telescope and Webb being perched much farther away from the Earth. If you'd like more information about Hubble and many of the things we're talking about today, we have some wonderful websites, nasa.gov/Hubble and hubblesite.org, and excuse me, ESA's spacatelescope.org website, and on social media, we are at NASA Hubble. All right, so with that, let's say happy 30th birthday to Hubble, and I would like to turn it over to our speakers who will give us more detailed information on each of these realms of science. Thank you very much. I don't know how. Okay.
All right. Well, we're celebrating Hubble's 30th birthday this year, but I'd like to highlight that this year also brings us the 25th anniversary of the discovery of the first exoplanet around the Sun-like star, which garnered a Nobel Prize this year. So the field of exoplanet science is actually younger than the Hubble Space Telescope. And so naturally, it was never a science case that was envisioned early on in its construction and then launch. Of course, it was mentioned that there have been many servicing missions that have brought new instrumentation to Hubble. None of these have actually been specifically designed to study worlds beyond our solar system. But we've been able to leverage them to get really detailed insights into these planets beyond our own solar system planets. And there are two ways that we really study exoplanets using Hubble. And the first is a technique called coronagraphy. Okay? And these are fairly basic coronagraphs on Hubble, but they do the job. You block out the star's light using basically a big hunk of metal, and then you look for faint things around it. This has been a workhorse for studying things like debris disks around other stars that are really leftovers of planet formation. But folks have been able to use these coronagraphs on the Hubble Space Telescope to dig deeper using a variety of techniques to detect and then actually follow planets as they go around in their orbit. The other way that Hubble has been leveraged to study exoplanets is to look at planets that transit their host star. That is, they pass in front of their host star as seen from Earth and also behind it. In this way, we can actually look at starlight filtered through those planet atmospheres to find out something about what's in the air around these planets beyond our solar system. So let me first touch on coronagraphy. These are some of the iconic images that I think folks have seen from Hubble that have shown us, our first views of these distant worlds. Those are actual planets around other stars. And in many cases, with the image on the left, these were basically images that were taken before we knew those planets were there. And then enhanced post-processing techniques came along, and we were able to dig back into the archives of these data and find planets that were just buried before. And so I'd like to highlight that Hubble offers us a huge legacy archive of data that still can bring forth new discoveries today. Now, I also want to highlight that Hubble brought us our first detection of an exoplanet atmosphere. Soon after the discovery of the first planet that transited its host star in 2000, folks immediately thought, hey, we need to use Hubble to look at this planet and see if we can see any hints of sodium in its atmosphere. And so that's exactly what they did. They used optical instruments on Hubble, were able to look at the planet as it passes in front of the host star and see just a tiny little extra bit of absorption that indicated the presence of sodium in that planetary atmosphere. This technique we call transmission spectroscopy has been leveraged now about 100 times to probe a broad variety of exoplanets, looking for things like water, sodium, and potassium. It's also helped us to reveal both cloudy and clear atmospheres, worlds that are shrouded in haze. And Hubble has been the first facility that has given us this very, very unique view into the atmospheres of planets beyond our solar system. And this is actually, I would like to say, heralded in the era of comparative exoplanetology. It's the first time that we've been able to get a large enough sample of planets where we have good spectra, where we can tell what their air is made of, how much clouds they have, how much water, that we're starting to understand trends in these gaseous worlds largely. But I also want to highlight that Hubble's unique ultraviolet capabilities has shown us that there's a lot of atmosphere escaping from many of these worlds. And so I just want to highlight that the ultraviolet capabilities are really key for understanding processes like atmospheric escape, where you see hydrogen billowing off of these worlds, which causes them to actually grow smaller. And so Hubble has helped us to understand that in some cases we may have had worlds that were much larger, lost some of their atmosphere over time and become much smaller, which has helped us to better understand this huge population of what are called mini-Neptunes and super-Earths that were discovered by Kepler. Hubble has also mapped distant worlds spectroscopically. So we've watched planets as they go throughout their orbit, and using the near-infrared capabilities of Hubble, which are perfectly aligned for looking at these very hot gaseous worlds around other stars, we've actually been able to map out their temperature distribution and the differences in terms of water abundance on their day and night sides. Hubble has also shown us the color of the skies in other worlds in a way that no other facility will be able to do in the near term. So we've been able to look at these worlds as they reflect their starlight off of their atmospheres. And they have shown us that they have a variety of different colors, including HD 189, which appears to be a deep blue or purple. Hubble has provided us our first probes of habitable zone worlds. So we've looked at both the TRAPPIST-1 system, all the planets in the TRAPPIST-1 system, and other systems like K2-18b recently. And we've tried to look for hints of water vapor in their atmospheres, or actually signatures atmospheres escape, again, that UV capability. And so this is giving us really key insights into what makes a planet habitable, even if it's located in the habitable zone of its star. So Hubble will continue to play an important role, even in the era of JWST, even beyond. It's important to remember, as was highlighted, that the James Webb Space Telescope will really focus in the infrared wavelengths. Now that's great for looking for molecules. It's great for looking for light emitted from planets. But if you really want to get a handle on the full complexity of a planetary atmosphere, you also need the complementary information from those shorter wavelengths at ultraviolet and visible wavelength range. So they're going to tell us something about atmospheric escape, clouds and hazes, atoms, and other molecules that are just going to be inaccessible to the James Webb Space Telescope. And so I see a very rich field of study ahead of us as we get combined information from both Hubble and the James Webb Space Telescope to paint one of the clearest pictures we can of these distant worlds.
Thank you. I'm going to talk to you a little bit about Hubble science within our solar system. And one of the first things you might be wondering is, why should we use Hubble to look at stuff in our solar system? Don't we send missions to everything in our solar system? This little graphic, every one of those lines is a mission. It's gone to all of these different planets. And let's just talk about Mars. This is the family portrait of things that have studied, orbited, landed on Mars. Why in the world would you ever need to use a telescope to look at Mars when you've got all this in situ stuff? And the answer is that Hubble has a unique perspective on Mars. We can see the entire disk of the planet, and we've been able to watch it for going on 30 years now. So we can watch the changing, evolving atmosphere of Mars and use that as context for the spacecraft that are roving, orbiting, and taking other kinds of information. So Hubble is very complementary. On the side you have, the reason Mars changes its shape, its size, is that you're looking at Mars at its closest opposition to Earth every year, which is different. So some years it's closer to us, some years it's further. But what I find most fascinating is look at the poles. Look at how the poles evolve with time. Look at the atmosphere changing with time. And I have some recent images there. I want to, just so you can get a sense of how dynamic this atmosphere is. So it's global context. I want to focus on that one image to the far side, to the far right, in 2001. Because here's two images taken of Mars in 2001 by the Hubble Space Telescope just a few months apart. And what has happened is that the planet has been enveloped in a global dust storm. And by having these images from Hubble, we are able to interact with our spacecraft who are on the surface and give them a heads up. Hey, dust storm is coming your way. You may want to shut some things down. Or it could be, hey, things are clearing up now, time to open up again. So Hubble has been a really powerful tool for complementing the Mars spacecraft. Mars, of course, is not the only object. We talked a little bit about the ultraviolet. The ultraviolet imaging capability of Hubble has been a bonanza for studying the auroral activity on the giant planets in our solar system. When the Cassini spacecraft was in orbit around Saturn for 18 years, it relied crucially on the Hubble observations of the aurorae to understand the interaction of the sun's solar wind with the upper atmosphere of this planet. And these data were combined with the in situ spacecraft observations being made by Cassini to give us a clearer and more comprehensive understanding of how this planet's upper atmosphere varies with time. And of course, Cassini is gone. It has been deorbited. It was a very sad day. I don't know if any of you watched that happen. I did. I cried when the signal went away. But Hubble continues. And so Hubble is continuing to make observations not only of the aurorae, these images seen here, but of the atmosphere of the planet itself and its moons, its rings. So the science rolls on with Hubble and will continue for as long as Hubble is operational. Likewise, you've seen this gorgeous image that Jennifer showed of the auroral activity on Jupiter. And you can see the footprints of some of the moons. These are being done concurrently as the Juno spacecraft is orbiting this planet. Juno, a fabulous mission, does not have the capability to do the ultraviolet imaging. That's not what it is designed to do. So again, these continue to be complementary observations to Hubble. So Hubble complements existing spacecraft. Another very exciting complementary mission was Hubble and the New Horizons spacecraft. Hubble actually discovered 4 of the moons around Pluto that the New Horizons spacecraft went and actually flew by and imaged. And for Hubble, they're just dots. I mean, at least they know they're there, but they couldn't learn things like the New Horizons could. I have a little graphic here showing you how these moons orbit and spin as they go around Pluto, and it's really fascinating to see that happening. And it was Hubble that found those moons for New Horizons to actually study. Hubble actually enables space missions. You know, when the New Horizons mission was launched, it knew it was going to Pluto, but it didn't know where it was going to go after that. And it was deep survey images with first ground-based telescopes, which were not fruitful, followed by surveys with the Hubble Space Telescope, which identified this tiny body. And then the New Horizons spacecraft was redirected to fly by this body, and that happened roughly a year ago. And this is an image, one of the images from New Horizons of this object, which has recently been renamed Arrokoth. And so a remarkable object at the very edge of the solar system, one of the primitive bodies that was, we think, a remnant of the formation of our solar system. And this was enabled by the Hubble Space Telescope. Without Hubble, we would not have these images at all. I wanted to mention spectroscopy because we show images all the time, but you know, astronomers, spectroscopy is our workhorse. This is what we really use Hubble for a lot. We share all these beautiful images, but the science from the spectroscopy is really the workhorse. And on the left is some spectroscopy of Europa. It's from the STIS, which is an imaging spectrograph. So you can see lots of little images of Europa, but underneath it you see the wavelengths. And that actually tells us the chemistry within the plumes of Europa and tells us what they're made of, the water, for example. On the other side is a comet. And this particular comet, that's not a Hubble image up above. It's from another small observatory. But the spectrum underneath, where the chemistry is defined, is from the Hubble Space Telescope. And there was a whole paper about all the comets that have been discovered, have been studied over the past few decades with the Hubble Space Telescope to do comparative studies of these primitive bodies. So it's very rich for planetary science. We cannot send spacecraft to every comet. I mean, we'd love to, but we can't. And so a tool like the Hubble Space Telescope is the tool that allows us to do this comparative science with many different comets, many different moons, many different asteroids. So I could only talk about a few things here. I'm running out of time already. I wanted to show you this. This is a very recent Hubble movie of the first ever interstellar comet that we have identified as impinging in our solar system. And Hubble got this series of images that you can see here that are animated to show you this object moving through our solar system. It's on its way out now. We mentioned Jupiter. I did want to say that with the 30 years of Hubble observations, we're able to track the size and the shape and the evolution of Jupiter's great red spot, you can see from the top to the bottom how it has been shrinking in size. Don't worry, though. We don't think it's going to go away. So it's going to stick around. We discovered features on the planet Uranus. This is a dark spot that was discovered with the Hubble Space Telescope. In 2006, it only lasted about a year. And we've been looking ever since. We have a program called OPAL, Outer Planets Atmospheric Legacy Program with Hubble, where from now until the end of Hubble's life, we will be studying Jupiter, Saturn, Uranus, and Neptune, and taking images like these so that we can get an understanding of the evolution of their atmospheres with time. Hubble has looked at asteroids that have been colliding with one another and breaking up into pieces. It has studied the moons of Jupiter, looking for those plumes around Europa. Another result that I don't think has gotten as much notoriety as it should is that Ganymede has auroral activity. That was imaged with Hubble. You can see that blue stuff there. And by looking at how those aurorae on Ganymede wobble as this moon goes around Jupiter, we've been able to infer the ocean underneath, how deep it is and how much ocean there could be, which I think is really a pretty amazing way to remotely study a sub-ice ocean on a moon around Jupiter. That's a Hubble result. And finally, my own science for the young folk here who maybe not know, we have watched fragmented comets crash into Jupiter, making Earth-sized impacts. And that has really changed our understanding of how dynamic our solar system truly is and put us on the alert that we need to be paying attention to cosmic impacts throughout the solar system and particularly here on Earth. So if I had to summarize what we've done and what we look forward to, Hubble provides mission context for ongoing planetary science missions. It complements, enhances, and enables other missions, helps us prepare for new missions. And the power of Hubble is that we can look at multiple objects, we can conduct multi-decadal studies, and we can do it at multiple wavelengths that are not always accessible. It's been a superb solar system explorer, and it will continue to be over the next, as long as it is working and as long as we're flying missions to solar system objects, it will be there doing that work. So I'm a lifelong Hubble hugger, and I'm looking forward to many more years of fabulous solar system science with the Hubble Space Telescope. Thank you.
It's launching. Good, so Ray, I took the title that you suggested and I kept some letters, but I noticed that most of the words seem to have changed. But I did want to emphasize and talk about deep fields with Hubble, because this has been an area where Hubble has done an amazing, unique job in so many ways. It's opened up the early universe in a way that no other telescopes have done or could have done in this time frame. I love this image. The Hubble as it was in 2009 after it was released after SM4. So the first deep Hubble image, actually, it was the Hubble Deep Field that was taken as a result of Bob Williams' interests in doing something unique with Hubble in the middle 90s after the servicing mission in 93 recovered Hubble. And it was a dramatic demonstration of what Hubble could do and nothing else that we had and ever seen before could have done. So in 2009, the last of the servicing missions, a new camera was put on, advanced camera was repaired, and Hubble was really beautifully poised then to carry out even better, deeper surveys that covered a much larger range in look-back times in looking into the early universe. And some of the first ones that were taken, there was the Hubble Ultra Deep Field, of course, which came out in 2003 with the advanced camera, but then we took a new image in the infrared and we combined those, and suddenly we were looking into galaxies in the first billion years, the first 700 or 800 million years of the universe. And so Hubble has allowed us to explore this region. If you look at this, you see these things, they always look red, but that's just the artifact of the way they're displayed in the images. Reality is early galaxies are going to be very blue. How blue? Not so sure, but this is sort of schematically meant to represent what these are more likely to look like. So in 2012, 10 years after the Hubble Ultra Deep Field was put together, we collected all the data that had been taken on that region. It constituted an exposure with the open shutter of 23 days of Hubble time. Over 50 days of Hubble was spent on this. 800 orbits and some several thousand images were all put together. This is the deepest ever Hubble image of the sky that has been taken, and it still is the case. So this is one of the baseline images that really lets us push back in time. Very deep, but a small field. But Hubble, of course, like all our telescopes, but particularly in the case of Hubble, is a time machine that's let us explore back over 13 billion years of time, through 97% of all time to, in fact, just to about 400 million years after the Big Bang. And so this is into a regime that we never thought, I think 10 years ago, never expected to be able to do with Hubble. We were thinking JWST was going to do this. So we're on the edges of cosmic sunrise when the first stars and galaxies formed in Hubble, and I'll show you the earliest galaxy that we have discovered soon. In addition to these deep fields, of course, we have been taking images of clusters of galaxies, and they provide a wonderful complement of being able to go even fainter or even to lower brightness objects, but they don't give us a lot of objects. So the complementarity between the deeper fields and the clusters is a resource that we've had to explore galaxies in the early universe. But one of the, I think, remarkable things that we found as we look back over the years, over the last 16, 17 years of data, was that each of the great observatories, Hubble, Spitzer, and Chandra, had all spent about 6 or 7 million seconds, it's a huge amount of time, on this particular region of the sky. This first was started as the Chandra Deep Field South. Riccardo Giacconi was the PI, I think, on this program back in the late 90s, and that defined a region in the sky in the southern hemisphere where deep images were put, and the Hubble Ultra Deep Field was put there, GOODS program, Spitzer images. So this has turned out to be sort of the premier place in the sky to go and collect data. And it is now the biggest field that we have. And in fact, it's about the size of this nearby astronomical object. And so in this field, there's some 250,000 galaxies. It covers a pretty large area, let me back up and just say, of course, that XDF, which is the extreme deep field, is in the center there. So it's small and deep. So this is like a pyramid of images, which enables us to look wide, brighter images, and go very deep for the fainter images. And so what the Hubble legacy fields and these similar fields give us is basically a history book for the story of how galaxies formed and grew through nearly all time. A lot of the emphasis has been on that first billion years, but in fact it takes us right through time, through the peak of galaxy formation, close to the present day. And so here was an example of galaxies that we selected from the field there, the Hubble legacy field, and that go back from a few 100 million years old to back to almost 13 billion years in this field. And in that 250,000 galaxies, you have large samples that you can look at the way galaxies grow and build up and change over time. So, of course, it's interesting to look and see what is the most distant galaxy that we've seen. And we were fortunate to identify some of these in one of the other legacy fields in the north. There are 4 galaxies there, Spitzer and Hubble together, suggested that these objects were at about 500 million years after the Big Bang, so some of the very earliest galaxies that we'd ever seen. And interestingly, when we went and looked in one of these in more detail with Hubble and got a spectrum of it, a very low resolution spectrum with a GRISM, this turned out to be at 400 million years. So this is the most distant galaxy we've ever seen, the earliest galaxy that we've seen so far. Of course, JWST will blow past this back into the era of cosmic sunrise when the first stars and galaxies were forming. but this is a dramatic demonstration of Hubble's power, in fact, combined with Spitzer as well. It was that combination that really made a difference. So what does the future hold for Hubble? Well, here is the James Webb Telescope, which is going to launch in 2021. This is actually, for once, a real image of the whole telescope. We've seen simulated pictures and images for a long time. Here is the full observatory with the sun shield deployed at Northrop in October. Amazing to see. So will JWST lessen interest in Hubble? Not in my view. I think Hubble has really unique capabilities, blue, ultraviolet, that really complement JWST. And in fact, as we look forward into the 2020s, I think we're going to see this triumvirate of telescopes, which are called NASA's greater observatories, the synergy suite of complementary greatest observatories, where we have Hubble with its particular and unique capabilities, JWST with its incredible sensitivity in the near-infrared and infrared, and then WFIRST is a telescope with a very wide field. That Hubble legacy field with WFIRST could be done in a few weeks and several times bigger, instead of taking 3/4 of a year of Hubble time to actually get that field. So the WFIRST is a phenomenally powerful facility as well, very complementary amongst all three of those. So I think the future looks great for our great observatories, and particularly for Hubble as well. So thank you.
In organizing this, I want to thank our speakers. It's amazing. We've worked very hard year after year on all the great Hubble discoveries. And this is only a part of everything else we've done with Hubble. So I want to finish up, and I think some of this is self-evident when you look at all the discoveries. So why is Hubble the cultural icon it is? And so let me give you my take on this. And I'll keep it brief because I could do a whole talk on this. But Hubble has endeared itself in pop culture. We always have these wonderful cartoons. Everybody loves Hubble. Hubble is known on a first-name basis. The question is, how did Hubble become so popular? You can see it in Times Square, on a U-Haul, and in Madison Avenue advertising. Somebody stole our name, and they're selling contact lenses. But, we know it on a first-name basis. But I thought it was interesting. Yeah, we were fodder for Weekly World News. But that said, I found this on the internet, Jennifer. This was a calendar with religious, biblical words linked to Hubble pictures for inspiration. Now, obviously, I think it's seldom that you can cross this bridge between religion and science. Sometimes they're at odds, but I can tell you the Hubble pictures are embraced, even by creationists. They think they solidify their theory, but I won't get into that. Hit the right button. Now, I was delighted. Hubble has made cameo appearances in a number of Hollywood movies. But I was delighted by Independence Day 2 because for the first time, the script says these pictures came in from Hubble, not NASA's Hubble or the Hubble Space Telescope. It's first-name basis. And Heidi, apparently some kind of force is pulling on Saturn's reins. And so if you see that, I don't know. So I had one reporter ask me, what was the grand marketing strategy for Hubble? There wasn't, and it's due to the perseverance of NASA PR, public affairs people, science communicators, the reporter community, and of course the scientists all working with us to weave a narrative compelling for the general public. So why is Hubble iconic? It reads like a movie script, okay? It has a story arc. The history, which I'll try to compress very quickly because Jennifer touched on some of it, the anticipation of launch, the $2 billion time machine, the optical failure, redemption with the servicing missions, more drama when it was canceled in the last decade, and a resurrection. And John Logston picked up on this. I thought this was one of the best quotes supporting this mission. The people who manage Hubble have done a wonderful job of identifying Hubble with the frontiers of knowledge and discovery. It's become an icon. Now, I have to gaze a minute. This was the launch back in 1990. I'm there with some esteemed Hopkins astronomers. Little did any of us guess what was laying ahead for us. At that time, Timothy Ferris wrote a wonderful editorial in the New York Times. And I want to come back to this idea that Ferris picked up on. Hubble is a work of art. It says more about us and the better we can know. And I would argue that's been the history of Hubble's cultural and civilization impact. I would argue a civilization changer. Now, it was humble beginnings. You can see the picture on the right is the first Hubble picture. The picture on the left was a ground-based. You can see the tremendous improvement. And then Jennifer touched on this. We went through the mirror problem, and we had some cartoons that drove everybody nuts. And even worse, I know this drove NASA people at nuts. We made a cameo appearance in Naked Gun 2.5 on the right. In the background, this is the Blues Bar. In the background is Hubble next to the Edsel. And they had a hemorrhage at headquarters, I'll tell you. Of course, Mystery Science Theater has no respect. They smashed the Hubble and it fell to the ground. Of course, there was resurrection in our story arc, the tremendous servicing mission due to the prowess of scientists and engineers to correct the optical problem. It made that first servicing mission crew pop culture heroes. They appeared on the 1990 show Tool Time, showing off their $1 million instruments for fixing Hubble. And Jennifer showed this, but with each servicing mission, we get a kick in the pants in terms of public interest. Astronauts in space, astronauts servicing, extremely popular. News coverage goes through the roof. And with each mission and a new camera, we get front page. This was the envy of NASA for many years. And melodrama. I love this picture, Jennifer. You can see our project scientists look around. Melodrama, and the things always don't go right on these missions, although I think with 35 spacewalks were really good. We had a stuck bolt, which is why Dave's going. And the melodrama over on the right, the last servicing mission, there was a rescue shuttle in the foreground on the left of that picture to rescue the launched shuttle in case the tiles were damaged. And this is straight out of a Hollywood movie script, right? Rescue in space. You've heard from all our speakers the tremendous science from Hubble. What amazes me is that the blue balloons, I don't expect you to read this, the blue balloons are what was sold to Congress and what we touted Hubble for doing back in the late 80s. The red balloons are everything we didn't expect, including dark matter, exoplanets, which are a huge industry. And all this discovery, last year we passed the threshold of 1,000 press releases from the Hubble telescope. So intellectually, we have kept stoking the fires on this, working with the astronomers to keep Hubble at the forefront of our knowledge of the universe. The bigger thing, reaching an even wider public, is the power of the image, as this quote does. Because images go directly over the science and just hit people, everyday people, with the awe and wonder of the universe. Hubble imagery has redefined the universe for a whole new generation, or generation of astronomy enthusiasts and the general public. The power of the image cannot be underestimated. Some people say you're just about pretty pictures. Well, sometimes, but they go a long ways. For those of us old enough to remember, before Hubble, the universe was a little more boring. You could get, in popular books, you could get mostly black and white pictures from the great observatories like Palomar and Lick. And there were some nice color images done by David Malin. But you'd have to go buy a book or send away for prints. That all changed with Hubble due to the internet. We flooded the world with jaw-dropping pictures, month after month, year after year. And this wonderful New York Times editorial from a few years ago compares us to the impact of the Apollo picture of Earthrise, except we've far outlasted the Apollo. So these pictures are everywhere. They really have redefined the universe for the public. And they speak to the public at a visceral and emotional level that goes far beyond scientific understanding. This was from a New York Times editorial, which I loved. It said, Hubble has discovered a new universe, and Garth touched on this, going at very high redshift. Discordant objects, cataclysmic disturbances. Hubble with a completely new eye on a much, I would argue, a much more sublime universe before the telescope was launched. And I can't emphasize enough, working with the astronomy teams, our imaging specialists gave tremendous reverence to the power of the image, combining the objective and the subjective with all Hubble's filters into pictures that capture the essence of celestial objects. I get tired when people say, well, is that what the color really is? That's not the point. We're really capturing through tremendous effort and again, reverence to the science. And I think this has really helped make Hubble a tremendous success for the public. Kathy Sullivan on the first Hubble servicing mission touched on this in an article just a few months ago. The way it's entered into the popular conversation, the popular culture, it's amazing the rich and artistic understanding of the universe that has permeated pop culture. This guy is great, and we didn't pay him to write this. This is a Philadelphia-based media artist. Hubble illustrates the power of human reason and cooperation, boundless creativity and curiosity. I couldn't write this better myself. And he gets even better. He says, all 21st century philosophy exists in the wake of Hubble. So how's that for, I love it. I'm going to put that over the door. So, so this goes back to Hubble's intellectual, cultural impact. I would argue a game changer for civilization's perception of the universe and our place in the universe. So, if I were to do a Netflix series on the story arc, the Hollywood story arc of Hubble, these are the episodes. You know, the amazing anticipation, the blunder, the comeback, of course, Space Odyssey's in there, the drama of the mission being canceled and reinstated, and of course, well toward 2030, we're back to doing some of the best science we think we can ever be able to do with Hubble. Okay, so thank you.
I don't know, if we were really on a first name basis with Hubble, we'd call it Edwin. All right, thank you all. That was great. So we've got a little bit of time for questions. So we'll start here in the room. We'll start with Dan. When Christine brings you the mic, please say who you are and who you write for.
Dan Falk, freelance. This was terrific, and of course we're here to celebrate Hubble, but I want to ask, a very sad question, and I know you've been asked before. What's the latest on the ultimate end of Hubble? How will it end? Is there anything new to be said about that?
Let me try to address that. So right now we're in the middle of what I think is a very good news story about Hubble. When the astronauts serviced Hubble the last time back in 2009, they not only put in new science instruments and repaired science instruments, but they also refreshed the gyroscopes and the batteries. We have redundancy on many of Hubble's systems. The gyroscopes, at the end of that servicing mission, we had 6 of them on board. Nominally, we need 3. But we can actually operate on 1 due to the ingenuity of the engineers with Hubble. We've lost 3 gyroscopes since 2009, but those are the 3 that had a different kind of flex lead than the ones that remain. The ones that remain have an enhanced flex lead system that should make them last much longer than the ones we've already lost. So the gyroscope situation is good. The batteries are very healthy. The science instruments, we have 2 instruments on there that I really thought would not be functioning by now. They were repaired in that servicing mission, and now they've operated longer in some cases than they were on board before they were repaired. So they're still operating, and then we have 2 newer science instruments on board as well that are doing very well. So the science instruments are in good shape. And NASA has basically committed to funding and supporting Hubble as long as it's being scientifically productive. So that looks bright as well, because Hubble is very scientifically productive. And as you've heard today, it's very critically complementary to other probes for the solar system and observatories, both ground-based and space-based, in the present and in the future, including the Webb Space Telescope, which will be a marvelous infrared observatory. But Hubble's capabilities are critical to have, in addition to James Webb, to have that full coverage of the electromagnetic spectrum. So we don't know how long Hubble's going to last, but as long as Hubble's being scientifically productive, NASA is, at least now, committed to supporting it. So I think that's good news.
Let me add one very brief emotional answer, not a technical answer. Someday it will do orbit. There's no doubt. I mean, we're committed to that. It's too big to let it fall uncontrolled. And I hope that when that day comes, many, many years from now, maybe even decades from now, we'll know where it's going to deorbit, and we'll all rent a big cruise ship, and we will all go on this cruise ship together, and watch from a suitable distance to see the deorbit, and we'll have an amazing party, and we're going to cry, and we're going to celebrate. We're going to give talks like you heard today, and we will just celebrate the amazing life of this fantastic telescope. I hope I'm around for when that happens, because I want to be on that cruise ship.
I should also add that while we have this marvelous suite of science instruments, some of which I didn't really expect to still be operating now, if we start losing an instrument, which will happen in the coming years, an instrument here and then another one, we will still be getting fabulous science out of whatever instruments remain on board. So we'll just rebalance the science portfolio based on the kinds of science that the remaining instruments can achieve. So we're already planning how to maximize the science return on Hubble depending on the capabilities that we have with it in the coming years.
Jeff Faust of Space News talked about the synergies of Hubble with JWST and WFIRST down the road. In sort of a more practical sense, any discussions about how that would work in terms of joint observing, syncing up the different observing cycles, doing simultaneous observations, things like that?
Yeah, let me just comment on that. So to some extent that's already been done with Spitzer and Hubble, and sometimes with ground-based observatories as well. So the community is used to having those opportunities, but I think also community folks are very imaginative about the way they build up programs and are willing to put in proposals to the multiple observatories to ensure that they get the complete data sets they want. So partly it'll be through opportunities and partly it'll be bottoms up, and from scientists who just think of a novel way to use the telescopes and bring it all together.
I'll just add, too, that we have been preparing for this with the Hubble Space Telescope, and we have been building up sets of observations that we know will be complementary to what will be done with JWST. For example, the ultraviolet, JWST can't do that. And so we've been preparing for this. And of course, as Garth said, once, hopefully they'll both be flying at the same time, and we'll be doing coordinated observations because we do that with many of our current facilities. It's going to be really, really exciting. I know that we're all looking forward to that.
Yeah, let me just add to that too, Heidi. That was a good point. I didn't think of that one. So the Hubble legacy field that I showed was spent, I said 3/4 of a year of Hubble time alone on that field. The vast amount of data there. And that's the centerpiece of a lot of the observing that will be done in the first year for James Webb. So already the James Webb, the plans are to build on that and to bring about those synergies such that we gain those insights into pushing back even further in time, but building on what Hubble has done.
There's a session here at this meeting on Wednesday, an entire session on how these two great observatories will be complementary to each other, with some really specific talks about how different realms of science will thrive by having both Hubble and James Webb operating together. And I don't remember whether that's Wednesday morning or Wednesday afternoon, but I believe it's on Wednesday. So I encourage you to look up that session.
Do we have any questions online, Dharani?
Nope, still quiet.
Okay. We'll take one from Govert here in the back.
Govert Schilling, freelance from the Netherlands. Could any one of you try to imagine how astronomers like 5 centuries from now would look back at Hubble and describe it?
5 centuries from now.
Well, I think some of the things that Ray talked about are encapsulating that for you. This facility will go down in the history books as a turning point in astronomy, where we have built a facility that revolutionized all fields of astrophysics that it could touch. It was designed to do certain things, but it was so powerful and so well constructed that it went on for decades in fields like Nikole field the people hadn't even imagined. I mean, they've imagined things like planets around other stars, but it was science fiction. And in the course of Hubble's lifetime, science fiction became science reality. And Hubble was a key player in that transition.
I think it's also very good to think about the fact that Galileo did his immortalized detections of motions in the solar system with his telescope about 4 centuries ago, more or less. So we can see how that transformed humanity's views of the universe, and maybe we'll look back centuries from now to what Hubble has done and have that same sense of historic appreciation.
But only if we address global warming.
Well,
I do want to pick up on what Jennifer said. I think the astronomy textbooks, many years from now, we're a watershed, just as Galileo was. And I think, again, the intellectual impact, cultural impact. Hubble's a very hard act to follow in terms of culture. Future observatories will do tremendous science. But this new eye on the universe, in parallel to Galileo, I think that storyline will survive for a very long time.
I think part of Hubble's power, too, you don't want to miss, was that it came of age at the same time that the internet came of age. And that took the explosion of imagery coming from Hubble and put it on the desktop and now in the hands of everybody in the world who has access to the internet.
I still remember how when anybody who hadn't heard of the web yet heard about it with the Shoemaker Levy 9, because basically the whole world watched those impacts looking over your shoulder. Yeah. And suddenly the internet was the place to gather for major current events as they happened. Yeah. All right, well, I hate to have to bring it to an end, but I do, because we've gone an hour and there's lots more stuff happening this afternoon. So let me thank Ray in particular and all of you for coming today. We do definitely look forward to many more years of great Hubble science to cover and to share in briefings here at AAS meetings. I want to remind the press corps that we have a reception hosted by the National Radio Astronomy Observatory this afternoon at 5:30 in this room. The next briefing will be tomorrow morning at 10:15. And I noticed that the time zone is HST. So all our briefings are HST. Yes. Right? And the topic of that one is things that go bump in the night. So I look forward to having all of you here and many more people as well. Thank you for those of you who joined us on the webcast, and we will see you tomorrow morning.